Alright, so the notes for today are on section 14.3. We're going to construct exponential functions. The goal for today is to be able to build these exponential models and to explain the rapid growth patterns. So we're going to start with a couple of definitions. In these exponential models, they're all going to follow the equation y equals a times b to the x power. And so we'll later talk about what the a is, what the b is, and then how you can evaluate functions for different values of x. An asymptote is a line that a graph gets closer to touching but never crosses over. And so we'll see how the graphs that we're going to look at today get closer and closer to these asymptote lines. For the exponential models that we're going to be looking at today, all of our asymptotes are going to start with y equals because they're all going to be horizontal lines. A function that's increasing means that it's going up, or the function values are getting larger over time. And then when a function is decreasing, it means that it's going down, or the values are getting smaller over time. And so those definitions are kind of going to provide a foundation to the examples that we'll look at today. Problem number 1 here gives us a function that we know is an exponential function because the x is up in the exponent. And for this function, we're given the domain is -1, 0, 1, 2, 3, and 4, and it's asking us to evaluate the function for those values. So when I plug these numbers in, I'm going to be plugging them in up here for the x. So this one, I'm going to do 3 times 1/2 raised up to the -1st power, and I'll simplify that. And then 3 times 1/2 raised up to the 0 power, and then I'll keep going, just substituting each of these values in for x. When you make a table with these numbers, just make sure I don't make any mistakes writing them down. There you go. When you make a table with these numbers, it's the same as we used to do when we had a straight line. It's just we know that this one isn't going to be a straight line because of the pattern of growth. It's going to get either bigger or smaller more quickly. So let's see. We could just type these into our calculator, and I would encourage you practicing how to do that. But I know that a negative exponent flips anything upside down, so this negative exponent will flip this fraction upside down. Let's see. It'll be 3 times 2, so I'll get out 6 for my answer. So this equals 6. That means the point that I'm going to put on my graph is going to be the point -1, comma, +6. So that'll be one of the numbers that goes on my graph. And then the next one, anything raised up to the power of 0 equals 1, and 3 times 1 is 3. And so the next point on my graph is going to be 0, comma, +3. And then I'll just keep going with these. Let's see. 3 times 1/2 would be 3/2. You could keep that as 3/2 if you wanted to, or if you preferred, you could write it as 1.5. It's the same thing. So 1 will go with 1.5. And then, let's see, this is going to be 3/4. You could change it to a decimal too if you wanted to. So it would be 0.75. This one will be 3/8, because again, you're going to cube the top, cube the bottom, and then multiply the 3 times the 1/8. And again, you could convert that to a decimal if you preferred, but I'll work in fractions. Let's see, 3/8 is a little bit less than 1/2. And then this one would be 3/16. And again, you could convert that to a decimal if you preferred. So what we have over here is we have a graph. It starts up high and then it comes down low. Each time you plug in a new number, the fraction gets a little smaller, and it's getting closer and closer and closer to 0, but it's never actually going to equal 0, and so that's helpful to note. Even though this graph is technically a discrete function because the domain was given to us, you can see the pattern for where the line would go through them. We're not going to draw it because it's a discrete function. Sometimes the lines are drawn erroneously just to give you the pattern, but we're not going to draw the line on it because it's a discrete function. But you can see where the line would go. There's a couple of things that I want you to notice about this graph. This point here, where the graph crosses the y-intercept, my y-intercept is 0, 3, and notice that it was a 3 out front when you started. Those two things are always going to match each other. This is where it starts, and then this is how much it changes by each time. The other thing that I want you to notice on this one Let's see, let's write down the note about the y-intercept. I'll write it down over here. So the y-intercept is the point 0, 3, because your a value out front is the 3. And then the other thing that I want you to notice is that the number inside the parentheses tells you whether it's going up or whether it's going down. If it's a fraction in between 0 and 1, that means it's going to be going down. And so this b value, or the number inside the parentheses for this one, b equals 1/2, means that I know that the function is going to be going down, because it means it's multiplying it by 1/2 each time, which means that it's getting smaller. Example number 2, the final one on the front page of the notes for today, has pretty much the same pattern. So here, the number out front is a 3, so I can go ahead and say that I know that my y-intercept is going to be the number 3. So I know that when I plug my numbers into the table, that'll be the point where it crosses the y-axis. And then I want to look inside the parentheses. So my b value on this one is the number 4/3. That's a fraction that's bigger than 1, and so since it's bigger than 1, I know that this graph is going to be going up. So it's not going to be coming down like the last one was. It's going to be going the opposite direction, and it's going to be going up this way. Let's see, the domain is given to me, so I'll go ahead and plug these numbers in. So it's going to be 3 times 4/3 to the negative 2, and then 3 times 4/3 to the negative 1. And then this last one right here, where they got 7/9, they did the work for this one. I'm going to write it over it, sort of. They did 3 times 4/3 raised up to the 3rd power. So when you're finding the domain, you're going to plug all of those numbers in. Let's do the work for this one. Fractions flip, numbers upside down. And so this one's going to, you know what, you guys, these would probably be a good one to practice typing into your calculator. So feel free to do that instead of following along with me. When I do, let's see, 9/16. So this one's going to give me 27/16, which you would be more than happy to convert into a fraction. 27/16 is a little bit less than 2. So -2 will go with a little bit less than 2. And then when I do this one, I'm going to get 9/4. And 9/4 is a little bit more than 2. I already know the next one's going to give me 0, but I'll practice plugging it in. Anything raised up to the power of 0 equals 1, and then 1 times 3 is equal to 3, so 0 goes with 3. I already have that one on there. Let's see, this one will give me 12 divided by 3, which will give me 4. If doing the fractions for these and flipping things in your head are tricky, you can always remember, you can just type these into your calculator, but practice where you put the, how you raise the number up to an exponent. You definitely want to know how to do that in your calculator. Let's see, this one's going to give me 16/3, which is a little bit more than 5. And then this one is going to give me 64 divided by 9. And 64/9 is the same thing as 7 1/9, so you could understand that in the same way if you preferred to keep it as an improper fraction. So when I plug in a 3, I get out a little bit more than 7. The curve is a little bit harder to see on this one, but if you notice, the points aren't in a straight line. They are bending and curving and moving upwards, and so that's how you know that it's an exponential function. Remember, we're not going to draw the curve through it, because it is a discrete function. They gave us the domain, and anytime the domain is given, we're not going to draw the curve through it, but we could draw the smooth curve that connects these points and that continues going upwards in an increasing way. Question number 3 is having us practice exponential functions that are given to us as word problems instead of as equations. So we want to figure out 2 things for each one of these functions. Remember that the form of an exponential function is y equals a times b to the x power. The a is the number that you start with, and then the b is the multiplier, or you can also think about the b as being the common ratio if you think about what we did in the notes yesterday. You also want to think about the fact that the a is also your y-intercept. So for these two problems, we have to figure out what the a is, and we have to figure out what the b is, and then we can use that to write the equation. So in the first one, it says you're taking a piece of paper and you're folding it in half, and every time you fold it in half, the thickness of the paper doubles. That means that your b is going to be 2, because every time you fold it in half, it gets twice as thick. It tells you that the unfolded piece of paper starts at 0.1 millimeters thick. The total thickness T of n of the paper is an exponential function of the number of folds n. Write an exponential model that represents the situation. We could start it with y equals, but this says T of n, so when I write my equation for this one, I'm going to write, instead of y equals, I'm going to write T of n is equal to, and then to model what's going on in this problem, I put the a value in first, so that's the starting value, that's how big it is when you start, and then every time you fold it, it says you multiply it by 2. So if I folded it once, it would double. If I folded it twice, the doubled value would double again, and so on. And so this model right here is the equation that represents what's going on in the problem. In question number 4, we're asked to do the same thing. This one says a savings account with an initial balance of $1,000. Initial means that's how much it starts with. So for this one, it says it's starting with $1,000, and then it tells you that it earns 1% interest per month. So if it earns 1% interest per month, it says it's going up every month. You would multiply it by 1.01 to get it to go up to the next number. The account balance in dollars B of t is equal to an exponential function of time t in the months after the initial deposit. Write an exponential model that represents the situation. So for this one, you're starting with $1,000, and then every month, to figure out how much money would be in the account after that, you would multiply it by 1.01. That would cause the 1% increase. In both of these problems, all we were doing was creating the function. A function could also ask you to look at the equation given and pull the important information out of the question. So on both of these, I want you to label that this is what it starts with, and then this is the multiplier, or what it's multiplying by each time. Same thing on this one. In this exponential function, this is the start value, and then this number over here in the parentheses, this is the multiplier, or what you're multiplying by each time. Notice that on this one, your b equals 2, and so that's how you know that this function is going to be getting bigger. The function value is going to be increasing. It's going to be going up because the number inside the parentheses is bigger than 2. It's going to be an example of exponential growth. And then on this one, your b is equal to 1.01, which is also bigger than 1, which means that as you go over time, this function is also going to be getting bigger. If the number inside the parentheses is a number that's in between 0 and 1, it means that the function is going to be getting smaller. It's going to be an example of something called exponential decay, and we'll practice that more in the coming days. This section, number 5, problem number 5, can be tricky for some students, and so I want to make sure that you see why we're doing what we're doing here. Back when we did y equals mx plus b, we could do the same process with linear equations, and so we're doing the same thing, but we're doing them with exponential equations. So, in order to use the form y equals a times b to the x, you have to be able to know what the a is and what the b is. And sometimes you can figure that out right away from the information that's given to you in the question, and other times there's a little something that you need to do. Remember that your a is your starting value, and so on this one, they give you your a right away. Your a is 3. Your a is also your y-intercept, and so if the problem gives you a point with 0, then you know that that's going to be your a value. To figure out your b value, some people like to write the points in a little table. So they'll say 0 goes with 3, oh here's your x and here's your y, and then 1 goes with 6. Some people like to do this to figure out what their b value is. Remember, the b value is what you take to multiply this one by to get this one. So in this first problem, to make a 3 turn into a 6, your multiplier would be times 2. And so you can use the table to help you figure out that your b would be 2. Once you know that your b is 2, you have enough information to write the question. So the a goes out front, the b goes inside the parentheses, and then the x goes up in the exponent. This is the answer to the question. So this says that you start at 3, or your y-intercept is 3, and then it says that to get the next number in the list, you would multiply the 3 times 2. Keep in mind that you can always plug this number 1 in right here to figure out 2 to the first is 2, and 2 times 3 is 6, and so it works because it gives you back that answer. We can do the same thing on this second example. So they give me 0 goes with -2, so that means my starting value is -2. And then to figure out my other numbers, let's see, 0 goes with -2, 1 goes with -5. So this one's a little bit trickier because it's harder to figure out what you multiply a -2 by to turn it into a -5. Notice that it started negative and it's staying negative. So the number I'm multiplying by is going to be a positive number. Anytime you're having trouble figuring out what you multiply a 2 by to turn it into a 5, remember you can always do the opposite and you can work backwards. So you can take -5 and divide it by -2. Remember, I'm working backwards to get the answer to the question. -5 divided by -2, you could either keep it as 5 over 2, or if you wanted to, you could change it to a decimal. And so for me, you can do this either way. My multiplier, the thing that I'm multiplying by on this one, is 2.5, and so my equation would be -2, that was my starting value, and then it's going 2.5 to the x power, and so this would be the equation that would get you the next number in the list. It's also correct if you put 5 over 2 inside the parentheses right here. Either one of those would be accepted as correct. The next two problems have a little bit more work because they don't give you the 0 value, so we're going to have to go backwards and figure out what that 0 value is. Here, let me just adjust the paper so it's easier to see it on the screen. Alright, we have to figure out what our a is. We're not sure, so I'm actually going to start on this one by making a table, but it starts with 3, so I'm going to leave space for 0, and space for 1, and space for 2, and then I'll say 3 goes with 12, and 4 goes with 24. From this, I can figure out what my b value is, because to turn a 12 into a 24, I multiply by 2. So I know that my b is going to be 2. And then once I know that my b is 2, I can work backwards to figure out each of the previous numbers in the list, because I would just be dividing. So to go backwards to figure out this number, when I divide by 2, I would get 6. And then I would divide by 2, and I would get 3. And then I would divide by 2 again. And you could write it as 3 over 2, or if you wanted to, you could write it as 1.5. It doesn't matter which way you write it. So this one is going to be y is equal to, remember the a goes first, so this is where it starts with at 0, and then the pattern is that it's doubling each time. The last one on the notes today, let's see, they give me the number for 1 and the number for 2. So when I make my table, I'm going to have to leave the space for 0 because I'm going to have to go back and figure out what number goes with 0. If 1 goes with 3, and if 2 goes with 9 over 4, this one again, it's a little bit tricky to figure out what number you have to times a 3 by to turn it into a 9 over 4. So on your calculators, you could always change this into a decimal if you wanted to, 2.25, or if you wanted to, in your calculators, you can do 9 over 4, and you can divide it by 3. And you can type that fraction into your calculators. So you could do 9/4 divided by 3. And when you do the work for that one, you're going to get as a fraction, it's going to turn into 3 over 4. Or if you wanted to, you could write it as 0.75. Either way would be accepted as fine. So you guys, to get from this one to this one, I multiplied it by 3 over 4, or by 0.75. So when I work backwards, I'm going to have to do the opposite, and I'm going to have to divide it by 3 over 4, or I'm going to have to divide it by 0.75. And again, you can do the work for that one on your calculators. When you type it in, let's see, dividing it by 3 over 4, you're going to get 4. So 0 goes with 4. My equation for this one, when all is said and done, remember, I didn't write down my a value. So my a value is 4. And then the number that goes inside the parentheses, you can put either the fraction or you can put the decimal. So 0.75 raised up to the x power. But again, that number inside the parentheses could also be the 3 over 4, the fraction, and that shows you if the the number that you're multiplying by. To wrap up this section, I just wanted to give you a little preview of how these things work. Remember, you can look inside the parentheses. So this one has a 2 inside the parentheses, which means this later will be an example of exponential growth. Growth just means that it's getting bigger. This one has a 2 inside the parentheses as well, so this one will also be an example of exponential growth, so it's getting bigger. This one has a 2.5 inside the parentheses, so this one will be an example of exponential growth. And then the last one, I want you to look at the number inside the parentheses. This one's 0.75, which means that this one we'll practice. It's going to be an example of something called exponential decay, because the 0.75 means the numbers are going to be getting smaller over time.